This recording, we are going to use the example we did previously about the quadratic, using quadratic and semi-log regression model, but we are going to build new models using cross-validation techniques. To remind you about this, what we found from the previous video, watch the previous recording, we come up with the idea that the second model was better because it has higher r squared. The second model contains two extra terms. The first one was the age squared, and the second term was the log income transformation for the log. And we concluded that the second model, which is this one, was doing better. The first one was just containing the two linear model, the two variables only, right? So the happiness hat equals 0.22 age plus 0.00014 income. So we said the second one does better, and we did some predictions, but we said that, hey, what if how the model does in the unseen data, we don't know. That's why we have to do cross-validation techniques. So we're going to use the same example for that reason. So the first method we're going to use is holdout method, and we're going to estimate both models. We're going to estimate both models. So for you to understand what we're going to do here, it's recommended that you watch the previous video fully, then you move on here. To use the holdout method, let me just quickly say what we are going to do. We are going to divide the data into two parts. We're going to partition the data into two parts. The first one, we're going to call it training data. The second one, we're going to call it validation data. In this recording, I'm going to do the holdout method in the way that is supposed to be done. The book uses different techniques sometimes. He says that the book says, choose the first 100 to be in the training set and the second 300 or 200 or 50 to be in your validation set. That's why I'm not going to use this purposely selected samples. I'm going to create random samples. And because if you want to repeat, if you are watching this video right now, and you're going to get the same results that I am going to get, because now we are going to involve more functions that contains randomness. So if you do generate random numbers, you're gonna generate different random numbers that I do right now. To be all of us on the same page, we're gonna use a function called setSeed. Set.seed. Set.seed. We can set any number, any seed number, all of us, to get the same answers, which produces the same answers. So first of all, I'm going to say here, set a random seed for what? Reproducibility purposes. So set.seed, let me use number one. This is going to be, if you use all of us, set.seed number one, we're going to get the same results. We're going to generate the same numbers, we're going to get the same results. Because now we are going to have our data. Let's go back to my data again. Look at my data. We have 100 observation. We have 3 variables. Now we're going to divide this into 2 portions. This is the holdout method. This is the first step of the holdout method. So how to do this, what I'm going to do, let me just explain what I'm going to do exactly here. We have 100 observations, right? So the first function I'm going to use a function called sample. So it's very simple, sample. This sampling is going to select, I'm going to tell this function to select the first 30%, a specific number of values. So in this example, we have 100. So I'm going to ask the R, give me randomly 60% of this data. Randomly choose, because we have 100, choose 60 observations randomly. So randomly give me 60 or 70 observations. Let's say 60. Choose 60 of the observations in a random manner. This is what I'm gonna do first. So generate random indices or observations for the validation set, or for the training. You can choose, let me use training. So I'm going to call these training indices. I'm going to call this, when you generate random 60 observations, I'm going to call these train indices. I'm going to use function sample and I'm going to, the sample, it's going to be from the 100. The sample function contains many, what's so called, many arguments, comma. The second one I'm gonna call something called replace, false. Don't do replacement, just choose. If you choose index number 1, don't re-choose it again. And I'm going to have the third one is going to be my size. So give me 60 out of the 100 without replacement. So let me just train indices. So let me see these. So randomly, the function give me these indices, these observations. Observation number 50, observation number 84, 13, 37, 60, and so on. These observations, I'm going to put them together. Listen, I'm going to put all of the observations together in the training data now. Because the holdout, means that we are going to split the data into two parts. Now, create training and validation data sets. So the first data set, now we have the overall data is my data. Now I'm going to call the first one to be train. What is going to be into train? It's going to be all of my data. And this is subsetting. We are doing now subsetting, and you have to go back to the subsetting idea if you forgot. My data, comma, I'm not gonna have all of the observations. So we have comma, before the comma is the rows, after the commas of all of the variables. We will keep all of the variables, but in the first argument before the comma, we have to select the observations. Which observations you're gonna have is the train indices. These observations. Does that make sense? These values. Basically, this is kind of like a vector contains all of these, which is, it's kind of C parentheses 50, 84, 13, 37, comma, 60, comma, etc. So this is exactly what we have here. So we're selecting these, subsetting. Again, go back to the class, to the week number 1. For the validation, I'm going to have the rest. The rest. What does it mean by the rest? Oops. Minus these, the rest. So the training data contains these 60, the others contains the rest, which is the other 40. Here we go. Look here, we have training data, 60 observations with 3 variables, validation 40, and these are randomly selected. Now we have 2 sets. We built 2 sets. And we know the dimensions now. The dimensions, we have 60 observations for the training, and for the validation we have what? We have 40, right? There's no need to see this, by the way, every time. So the partition, let me just cut this. I'm gonna put these together. Cut here. So we are organized. Here we go. We have the partitions now. Now we have to build the models on the training data, on the data sets, not state. So we have to, now we're gonna use only the training data to build the models. First model is the linear model, which is L model, happiness, tilde dot. In the past, we used to say, oh, I'm gonna estimate the model using my data. Let's say estimate using my data, but now I'm not gonna estimate the model using all of the data. No, we're gonna estimate the model using only the training data. We call them train, right? Also, we're gonna do the same thing with the quadratic model. Let's call it quadratic with semi-log. So what we get, quad model, happiness, oh, what's happening there, by the way, income plus age. You can copy the previous one, age squared. We talked about the I function, then the log of the income. And again, we are going to create this model using the train data, right? After you are building models, by the way, I did not look at the summary for both. There is no need right now, because do you remember that to compare the models we are not using now, R squared, to assessing the models, the performance of the models, we are going to use something called SE, the root squared, the square root of the mean squared error. So what we are going to do now, so you have to understand this very well, that we have estimated a model on the training data. Now we would like to test the prediction power of the model on the data have never been seen by these models. So we're going to do prediction now. We're going to do prediction. So we're going to do predict. Let me predict for the linear model. We're going to do predict. Use the linear model or plug in the validation data into the linear model. Plug in this data set into the linear model. What is the linear model? The linear model is this. This is the linear model. You can write the model. You can write happiness equals intercept plus this number times the age, this number times the income. And what we are telling now, we are telling R that, hey, go to the validation data, this validation here. Go to this go to the whole thing, go to this data frame and plug these numbers into the linear model. So, by the way, the predict is going to look at age, it's going to look at the income, he's going to plug them into the happiness. R, the predict function, realizes that the happiness is the response, so he's not going to touch this. So he's going to just look at these and plug them into the linear model as we did before. So after that, we are going to get a prediction for all of the validation, for all of age and income, all of these observations. So we're going to get a happiness score. Listen, we're going to get a happiness score for age and income. No, we're going to get an estimated happiness score. Someone's going to tell me, oh, we have ones. Yeah, we know we have ones. But remember, we did not use this data when we estimated the model, when we built the model. So the model never seen these data. So we're going to ask the model, hey, look at the first guy. What is the happiness score based on your estimated model, the one that we built? So the model is going to give me a score for the happiness, right? And we're going to see whether this score is close to this one or far away. We're going to do this for all of these observations, all of them. Then we're going to calculate the RMSE, which is the difference between the happiness and the estimated happiness. Just to make it for you to understand, I'm going to do something. Let me just copy this. Let me copy this and paste it here. What we got? We got happiness scores. This is observation number 1, 2, 3, up to 40, because we have 40 observations in the validation set, right? What if you'd like to add these here, like a new column? We call it happiness hat, right? Let's do this. So I'm gonna call this, I'm gonna add it to the validation set. I'm gonna create a new one, happiness hat. So we're creating a new column into the validation set. This is, just to be very specific, this is for the linear model. It's a long, but that's a happiness hat for the linear model. Let's look at the validation. Look at the happiness hat, the predicted happiness for the linear model. Let's do the same thing for the second model. So let me copy paste. Happiness hat for the quadratic quad model. Now we're using the second model, the one that we added age squared and the len of the age. Let's go back to validation. We have, very good. We have, look. Just look. Let me repeat. This data set have never been seen by the model. The model was built using training, different set. This is training data. We have 60. So we built the model. We estimated a model, 2 models using this data. Then we went to the validation. We said to the R, hey, plug in all of these values, age and income, in these models, two models. What are the happiness score that you're going to get? He said, hey, we got these scores. Now we can compare, because we know in advance what is the happiness score for this set. We can compare all of them. We can look at all of them, which one is doing better. But this is not, this is not the way that we're going to do it. We're going to use RMSE. RMSE does what, basically? It just finds the difference between these two numbers. Happiness, the happiness hat of the linear model. Then we square it. Then we find the mean, and we take square root. It's RMSE. So this is what we're going to do. We're going to get the same unit. So we look at which one has lower or minimum error. So this is the second step now. This is the second step. After that, we compare which model does better. So to calculate RMSE, so it's just a formula, mathematical formula. First, let me look at the validation, happiness. I'm gonna subtract this value for the linear, right? By the way, if you don't want, let me delete, I don't want to confuse you. If you don't want to add these two columns here, you can delete this. You can give it a name, give it predict L model. You can call this one predict quad. Then how to calculate the, but at least we know what does this column mean, what does this one mean. Now this one is not added to any data frame. If you run it, it's not added. Someone's going to tell me, oh, but still there, still here. Yes, because we did not overwritten it. I mean, if you want to redo this, you can run the training, this one again. You run this, you have to rerun from here to down. I mean, you have to rerun the train data. This one, no, this one, yes, then this one, then this one, then you run all of these, because if you run the train, it's gonna like start from scratch. But now you're gonna see it, it's still there. No problem, we don't care, by the way. Now we have to subtract, but at least we know that this means the happiness hat of the linear model. This is the happiness hat of the quadratic model. So what we're gonna do to calculate the RMSE, this is a formula that just we have to use, which is the validation, which is the happiness score minus the predicted happiness score. By the way, I mean, let's be very simple. The happiness is y, is the value of y, right? So let me use, I'm gonna keep it, predict L model. Let me run this again. Predict L. So we're gonna subtract these, then we're gonna square them. After that, I'm going to find the mean of these, open parentheses, close parentheses. After you find the mean, you're going to take square root of this, square root, SQRT, parentheses, parentheses. That's it. Copy this, repeat for the second one. Validation happiness, the happiness in our validation set minus the predicted quad. So we subtract this minus this, and this minus this. Which one gives lower error? The second model. We can see it from here, by the way. This is closer to 86 than this. This is closer maybe to this than this, and so on. So in general, the mean of these values. So the second one gives lower RMSE. So what does it mean by having RMSE? As we said, we have lower error, predictive error. So the quadratic model is providing more accurate predictions on the validation set because of the lower RMSE, and this model contribute to improve predictive performance. And if this was your concern or your major goal is to minimizing RMSE, then you can choose the quadratic model. This is using holdout method. In the next recording, we're going to continue and do the k-fold cross-validation method and repeat what we have done. Also, I'm going just to summarize this here, so let me pause. So this is the summary of what we have said, and as I said, let's move to the next idea, which is implementing k-fold across cross-validation method. Thank you.